In this video I will show you how to recreate Zelda in a 2D engine. Now, don't get too excited, we can't recreate the entire game. It's too much for one video. Today I want to focus on a tiny but very important part, just the 2D character movement. No sword fighting, no items, no enemies, just the movement of the character on a single screen. But we will tackle input, we will tackle animation, and we will tackle collision detection with the environment. As we will see, even this basic functionality comes with a lot of difficulties. I regularly see projects struggling to pull off satisfying top-down 2D movement. So much so that today I will show you actually 4 different ways to pull off this effect in increasing levels of difficulty. We will start out with something for beginners. Around level 3 we will hit a huge problem, and then hopefully we will end up with a wonderfully over-engineered solution at level 4. Now I will be using the weapon of my choice, which is the fantasy console Pico-8, but a lot of the techniques I will show today will also work in other 2D engines. I'm Christian, this is Lasers Academy, let's get started. Zelda. There's so many different Zelda games out there, but for this video I want to recreate the look and feel of this Zelda. This is Legend of Zelda Link's Awakening DX for the Game Boy Color. It's one of the weirdest Zelda games out there. There is no Zelda. There is a girl, but she's called Marin. And also the protagonist isn't called Link, he's called PP. But the main reason why I picked Link's Awakening is because in terms of specs and resolution, it's very close to the engine I'm using, which is Pico-8. Now, have you encountered this before? You want to make a game like some other game, but no matter what you do, your version of this game never seems to live up to the original. There is something you just can't put your finger on, but for some reason your game looks like trash in comparison. Well, I want to let you in on a little secret. There is a special game dev technique that might help you out here. You get the money? Give it to me. Good. Here's the scoop. You can record the footage of the game and you can look at it. Wait, who is this? Have you been followed? That's right, you can use a tool like OBS to record any game, just make sure you're recording in 60 frames per second. And then you can step through the footage frame by frame to see what exactly is happening. Even basic video players like VLC have, frame by frame features. Even YouTube has a frame by frame feature. Now I am editing a lot of videos, so I will be using the editing software DaVinci Resolve. So I did record footage of Link's Awakening. I went through it frame by frame. I paid special attention to, how quickly PP is moving on the screen, how he collides with objects, how many frames of animation there are, and how quickly they change. I then tried to recreate what I saw as closely as possible in Pico-8 to learn the recipe for the secret sauce. Now, I'm not saying that Zelda is the only way to make top-down adventure games, but this kind of exercise is a fantastic way to learn yourself what to watch out for when you're making your own game. So let us start by getting the graphics from Link's Awakening into our game. Being a Game Boy game, all of Link's Awakening's graphics are built out of small 8x8 pixel tiles. And hey, that's the same tile size as in Pico-8. However, the protagonist and most of the in-game objects are built out of 4 of such tiles, resulting in an effective grid size of 16x16 pixels. I sometimes heard people refer to this as meta tiles. The meta tiles are 16x16 pixels. The game's protagonist, PP, has 4 walking animations for the 4 cardinal directions. And here's an amazing detail. All of those animations are accomplished with just 4 sprites. That's right, an average of 1 sprite per animation. Now that's the kind of efficiency we need right now. Now here's how it works. Each walking animation consists of really just 2 frames. The animations for walking up and down are accomplished by taking a sprite and just flipping it horizontally. Easy peasy. For the sideways walking animations, we do have 2 bespoke sprites, but we can get away by just drawing the left walking animation. And we can then create the animation for going right by flipping those 2 frames again. And then here's another clever detail. You see, in this game, PP can equip a shield, which is then reflected in the character's sprite. This is almost certainly accomplished by layering bespoke shield sprites on top of the base walking animation. And I love how in the upwards and downwards walking animation, the shield really breaks up the symmetry to cover up the fact that it's just one sprite that is flipping sideways. And I also love how the shield is facing the player when PP is looking to the right, but it's hidden behind his body when he's looking to the left. This sort of attention to detail really helps selling PP as a physical character. You really get the sense that he's turning around when you change direction because your eyes track the location of the shield. Now Pico-8 can totally pull off all these effects, the flipping and the layering of sprites, no problem. And those tricks are very important to keep in mind when you make your own game, for sure. However, today for our exercise, I really want to focus just on the walking around, so I decided to bake all of these effects into finished complete sprites. This leaves us with 8 16x16 pixel sprites. Now again, because this is a Game Boy game, you only get 4 colors per sprite. And for character sprites, one of those colors need to be even reserved for the transparency. So really only have 3 colors. You have a black color for the outlines, you have a whitish color for his skin and all the highlights, and you have like a middle tone for everything else. I don't want anybody to complain anymore that 16 colors are not enough. PP's character art is so crisp and beautiful with just 3 colors. Now recreating this in Pico-8 requires a couple of steps. First, we need to get the sprites into Pico-8. We could prepare them in Photoshop, we scale them so they have the right resolution and make sure that the color palette matches Pico-8's color palette. We could then save them as PNG and just drag and drop them in Pico-8. But I actually opted to recreate the sprites manually by just drawing them over inside Pico-8 sprite editor. I think this is a great opportunity to familiarize yourself with the pixel art and all the techniques used. This lets you discover tons of little neat details. For example, I really love how in the sideways walking animation you can see PP's hair flopping in the wind. This is just so cute. Remember, the whole point is not just to copy, we want to learn. Now, Pico-8's default background color is black, and black is also transparent. So in order to differentiate the transparent color in PP's sprite from the black outlines, I decided to change the background in the sprite into this pink. We need to later tell Pico-8 to turn this pink transparent and the black not transparent. Also, Pico-8's default green color is a little bit too bright, too vibrant for this kind of sprite. This is a common pitfall when trying to recreate, Zelda and Zelda-like environments in Pico-8. The green is a little bit too bright and too saturated. It doesn't have really good contrast with the other bright colors. It doesn't look natural. It's almost like this highlighter green. We see here how, PP's sprite is just like a little bit oversaturated and overexposed. Now there's a second green, this dark green, and we could use this instead, but if we use this, now it's a little bit underexposed and muted. That doesn't look right either. One possible solution is to use something like this here, color 13. That has a really nice middle value and good contrast. This gets you a really nicely balanced image. However, it's grayscale, and so we're gonna try a more advanced solution for this later. Let's leave it like this for now and let's put a pin in this. With PP's sprite in our sprite sheet, we also need some environment art, so I picked just some random sprites from the sprite sheet to draw a nice little grassy meadow, and I also have like this little bush sprite to have an obstacle that we can collide with. The bush in particular also needs a bit of a darker green color, so I used this color number 2, this dark red for now, and again we're gonna change this in a second. The sprites I picked are basically these outline sprites. We have a couple of sprites that include blades of grass, and we have also this is kind of like this little flower animation. Maybe we can pull this off as well. And this is all we need to create the background in a map editor. Again, I'm doing this manually and I'm not really trying to recreate any specific Link's Awakening screen. This wouldn't be really possible because the Game Boy's resolution is slightly higher than Pico-8's. I'm just creating a nice little background for our test purposes. This is still a fantastic opportunity to learn something about how the graphics in Zelda work. For example, did you notice that the bush has the same black outlines that PP's sprite has, but that black outline is never used in the other sprites. All of the floor sprites have the darkest color, this dark green. This is to clearly clearly differentiate which graphics show objects that you can collide with, that you can interact with, and which graphics show just, background tiles that you can walk over. Also, I love how this entire patch of grass is this solid green color. Just a few individual tiles with blades of grass on them sell this entire surface as a patch of grass. And the outline that sets apart this patch of grass from a sandy background adds to this illusion as well. I see a lot of devs trying to add too much detail to their grass tiles and trying to draw every single blade of grass. This often results in a very visually noisy picture. Zelda games are a really good example on how to achieve overall great readability by focusing on subtle context clues. I could sit here and talk about pixel art all day, but we really need to move on with the programming. So if you are interested in diving deeper into this subject, a channel I would recommend is Brendan James Greer. For example, his video on recreating Obi-Wan Kenobi as a Zelda game is an excellent insight into the kind of pixel art decision making involved in creating games like this. So here we are, all the graphics are in place. Now let's put down some code to put them on the screen. In the code, I create the _init_draw and _update function. In fact, I'm going to be using the _update 60 function because we want to be running in 60 frames per second. More on that later. For now, we are mostly interested in a draw function. That is where we put stuff on the screen. And this is also usually executed at 60 frames per second. Now we can draw the map with just a simple call to the function map. That will just draw the map to the screen. I'm going to save this by pressing escape and typing save Zelda. Escape brings us back to the editor, and Ctrl-R will run this. Yes, this is our background, this is what we created. Now let us get our PP in here. This is like the VW loop of a joke. It's pretty bad, but I'm getting a lot of mileage out of it. So we draw our character right after we draw the map, and we use the SPR function. We open the parentheses, we first type 0. That is going to be the number of the sprite. This is the top left corner of our sprite. It says 0 here. Then we type comma 64, 64. That is the X and Y coordinates of where the sprite is supposed to be on the screen. X means how far it is from the left edge in pixels. Y means how far it is from the top edge in pixels. 64, 64 is roughly the center. Now we close the parentheses, Ctrl-S will save again, Ctrl-R will run. And there's a lot that is wrong here. For starters, this is a small sprite. This is not our full character sprite. Where is the rest of it? This is actually something I get asked a lot. What if I have a big sprite and I want to draw that big sprite? Well, you can of course draw all those individual sprites separately by using their own SPR commands. But there is an easier way. We just add 2 more numbers at the end of the sprite call. The first number tells us how wide the sprite is in sprites, and the second one tells us how tall it is in sprites. 2, 2 means we're going to have our 16 × 16 pixel sprite. We're going to have this area. We save this, we run this, and we have the full sprite in here now, but it still looks bad. The transparency is all wrong. So let us jump into this first function, the init function. Whatever is in here gets executed once at the beginning of the program when you launch the game. This is a good place to get our colors right. We can use the PAL-T, palette transparency function, to set the transparency of individual colors. First, let's make the black opaque. 0 is the black color, and then go comma false for not transparent. This will make black opaque. Save this, run this, and indeed we see now the outlines of PP. Now let's get rid of the pink. That is working the same way. We're just going to copy this line over. And now we have to find out what number the pink color is. We can go over to the sprite editor. When we hover over the pink color, we see it says 14 in the corner. Pink is number 14. And we are going to set this to true, meaning yes, it is transparent. We're going to save this, we're going to run this, and indeed this is looking way better now. Our beautiful baby boy. Okay, now I want to add the thing I was talking about, so strap yourself in. This is going to be a little bit advanced. So yes, I said that the green's a little bit too vibrant. Well, Pico-8 has some special extra colors, hidden colors, a hack, so to speak. And quite often those secret colors are actually just darker versions of the regular colors. So let's do that real quick. First, we need to activate the hack. And there is a special function for this. It's poke 0x5f2e, 1. This activates the secret colors, but we don't see them yet because we need to swap out our existing colors with the new colors now. And the way we do that is we use the pal function. So the pal function replaces one color with another. First, let us find out which number this radioactive green is. That's this, color 11. So 11. Now we need to replace it with the special colors. The special colors are the same number as the normal colors plus 128. So 11 plus 128. And there's one more thing. We have to do a comma 1 at the end. The comma 1 at the end is necessary to apply this as a screen palette, not a draw palette. It's a whole story. Don't worry about it. We're going to save this, we run, and now we have a much darker green color. This looks a lot more natural. Now let us also replace the dark red color in the bush as I talked before. So we're just going to copy this line, and the dark red color is the number 2, and I want to replace it with number 3. We're going to save, we're going to run, and you see this makes the bush stand out so much more. This is our game. And yeah, as a side effect, the colors in the editor are starting to look a little bit funky. Don't worry about it, it's fine. Now, if this was too fast, I have a whole video explaining the alternate color palette in great detail. It doesn't really matter that much for the rest of the video because we're not going to touch this anymore. And as I said, you can just pick different colors. As I said, you can just pick color number 13 and leave out all this new stuff that we just introduced here. This will keep your code extra simple. All right, let's get down to business. But before we do, a word from our sponsor, which is you. That's right, this channel is supported exclusively by listeners on Ko-fi.com. Big thanks to everybody who makes this show possible. And if you out there want to chip in and join the effort, the address for that is Ko-fi.com/lazydevs. But if you're not ready for this kind of commitment, I completely understand. Consider maybe subscribing to this channel. Let YouTube know that you are interested in this kind of bespoke game dev material like this. Anyway, I want to focus on our protagonist walking around. As I said, we're going to do this in 4 levels of escalating difficulty. Feel free to jump in at any level that is appropriate for you. There will be chapter markers below, and let's start with level 1. You are starting with Pico-8, you just want to have something on the screen moving. Here's the fastest way to pull this off. Our protagonist is currently being drawn on the screen on these coordinates, 64, 64. If we want to move our character, we need to change those numbers. How are we going to do this? We do this by creating variables. In the init function, we're going to create 2 variables, px for player x or ppx. We're going to say equals 64, and we're going to create a second variable py, ppy, and we're going to set it to also 64. The equation sign puts this number inside the variable. And you see how the number turns blue, and there's also other things in this code that are blue as well. Whenever you see something blue, that means that you could also substitute a variable in here to make the variable drive this property. So if you write px and py instead of the 64 in the sprite function, now those variables are controlling where the sprite is being drawn. Now if we save this and run this, nothing changes. It's still the same because right now we have the same numbers in those variables. If we want the sprite to move, we have to change those variables. So let's jump over into the update 60 function. This function is also being executed 60 frames per second. This is usually where the game logic goes, where we respond to button presses and move things around. Now watch this. If btnp left arrow close, then end. This character might be a bit confusing. This is a left arrow. I did this by pressing Shift and L. And you can also use this with R, U, and D for right, up, and down. And this whole line means that if the button left was pressed, then everything that's between then and end gets executed. Everything we put in here will be run if we press that button, at least for the frame that we press the button on. All right, so we want to actually walk left here. How do we do this? By taking our variable px, that's the x position of our sprite, and we go equals px minus 16. We take whatever was in the variable px, we subtract 16 from that, and we put the result back into variable px. And this is how we can walk left. I'm going to save this, I'm going to run this, and beautiful, we are walking left. Now we went off screen, we cannot return because we cannot walk into those other directions. How do we do this? Easy, we just repeat this 3 times for the other directions as well. Now, for going right, we need to add 16. For going up, we no longer deal with X, now we deal with Y. And for going down, we also deal with Y, and we also need to add. I'm gonna save, I'm gonna run, and now I can walk around on the screen. Isn't this sick? Okay, but now PP is always facing us, he's not turning around. How do we do this? Easy, we can also change the sprite. You see how the sprite number also is a blue number. That means we can also put a variable in here. Let's do that. Let's call this variable PSPR, PP sprite. And we set it to 0, and we can take it and put it into the sprite command. And now whenever we press one of the buttons, we can change this variable as well. When you go left, we want the character to turn left, and that is going to be sprite number 4. So we're going to set PSPR to 4. When you go right, we're going to set the PSPR to 8. That's the top left corner of this sprite. When you go up, we want to set PSPR to this sprite, 12. And when we go down, it's going to be 0. We already had that. Let's save this. And now we can walk around, and PP is turning around. Wonderful, beautiful, peachy. So far, so good. There's one last thing that we need to do to get our basic movement. Our PP character is not colliding with the bushes. He just walks straight through. How do we do collision detection with the bushes? Well, this is a bit of a multi-step process. Let me break it down. Whenever we walk, we look where are we about to walk into. If that place turns out to be a bush, we abort. We stop the walking, we collided with a bush, and there is no walking. So first things first, how do we find out what the tile is at a certain location? Let's just find out what tile we are currently on. And just for testing purposes, let's just print this to the screen. Follow along here. We're gonna go to the draw function, and we're gonna type in the following. Print hello world 887. Save, run. This is what it looks like. Now we have the text hello world in the top left corner of the screen. The print command, the print function, prints stuff on the screen. This is what we are printing. Remember the quotation marks. And 88, this is the location where we're printing it. 88 is pretty far in the top left corner of the screen. The final number, that is just the color that we're printing. 7 is this here, is this white color. Now, instead of this text, we want to print the tile that we are currently on, the number of the tile that we are currently on. And there is a function for this, it's called mget, map get. And we have to supply it with a coordinate. We're going to supply it with px, py, and this will return a number. So let's store this number into a variable. Let's store this into a variable called myTile. And we can take this variable and replace this text with this variable. So now it will print whatever is in this variable to the screen. Let's save this, let's run this, and it's not working. It's a 0. 0 means it's somehow not reading the tiles unless we move to the top left corner, and suddenly we're getting something. We're getting something in here. There is some numbers that we get in the top left corner, but nowhere else. What is happening? Okay, I want to showcase this because it's a common source of confusion. Px and py are the variables that store the position of our character in pixels. Now, mget will return the tile at a certain coordinate, but that coordinate is measured in tiles. Yes, in tiles. In the map editor, you see the bottom left corner. This is the coordinates of those individual tiles. And each of those tiny tiles is 8 times 8 pixels in size. In order to convert our character coordinates into the tile space, into the tile system, into the tile units, we need to divide by 8. So the solution is inside px and py, we divide by 8. This will take whatever was in px and py, it divides it by 8 and puts the result into mget. It doesn't actually change px and py. Py and px remain the same. I'm going to save this, I'm going to run this, and now you can see, now we're getting some numbers in here. We're getting some numbers. When I walk over different tiles, I'm getting different numbers. So for example, if I walk over a bush, I see a 41 in the corner, and that just happens to be the top left corner of this tile. It says 41 here. This is indeed giving me the number of the tile in the sprite sheet that we're currently on. At least the top left corner of our character is currently on. All right, we have set up our test, it works. Now let's set up a system that checks if we are about to move on a tile that has number 41, and if that's the case, we're just not going to move. In order to see where we're about to move and not where we currently are, we should have maybe a new set of variables. Let's declare them here in the update60 function. We're going to call them new x and new y, and we're going to set them to px and py for now. Now, in each of those if statements that we have here, we're going to put those new variables in front of the equation sign. So new x instead of px here, and new y instead of the py here and here. I'm going to save this, I'm going to run this, and now we cannot walk anymore. This is correct. Don't panic. This is what we wanted. What happens now is that the coordinates where we want to move to are saved in this new set of variables. And in order to actually move there, we need to approve it. And the approval looks like this. Px equals new x and py equals new y. These two lines are the approval of the new coordinates. And if we do this, it works now correctly. All right, so now let's make this approval contingent on whether we are about to move on something that is walkable or not. We're actually going to take this code that we have up here, and we're just going to copy this over. I'm going to copy this my tile thing. I'm going to put it down here. This is what gets the number of the tile. But instead of px and py, we need to use new x and new y because we want to get the number of the tile that we are about to move on. And then I can do an if statement like this. If my tile is not equals, this means not equals 41, then, and then we put the approval lines in here inside this if statement. So if the tile that we are about to move on is not 41, that is the bush, then we approve the movement. I'm going to save, I'm going to run, and indeed I can move around now, but I cannot move onto the bushes anymore. We have achieved collision detection, ladies and gentlemen. We have achieved it. All right, one more thing, and this is going to be a little bit more advanced, but very useful. In a real game, we're going to have a lot of other things that we can collide with, not just bushes. There's going to be pots, rocks, walls, chests, cliffs, all sorts of cool things. And all those things will have different sprites, not just sprite 41. So it would be great if there was some kind of universal system to mark certain tiles as not walkable. And wouldn't you know that Pico-8 actually has such a system. If you go to the sprite editor, you will see that there is this row of little lights, and you can turn them on and off by clicking on them. These little lights are saved for every single tile. We can mark every single tile with these lights. They are called flags. So something I can do is I can turn on the red color, the red light, for all of the tiles that belong to the bush. This is flag 0, and it says so in the bottom left corner. So now this flag, that is indicating to the system that this is not walkable. But the system doesn't know that. We have to code this ourselves. And for that, we need to rewrite our collision detection system somewhat. So currently, we are getting the number of the tile that we are about to walk onto. Now, there is a function that allows us to check if a certain flag was set to the tile with a certain number. That function is called fget, flag get. So something we can do is we can take this fget and put it inside this if statement. And we're going to say, open parentheses, my tile, comma, 0 equals false. This means that if for the tile number that we found, the flag 0 is not set, is equals false, then we approve the movement. By the way, you have to use the equals to compare things to each other. Single equals sign means assignment. Double equals means comparison. Very common source of errors. We save this, we run this, and indeed this works perfectly. And I can even test it by making sure, for example, that I set the red flag for the little flower. Let's do that real quick. Bam, red flag, saving. And indeed, now the flowers are no longer walkable. Now these are obstacles too. Let's turn this off again. I actually want to walk over the flowers. And in fact, let's clean up this number printing that we did up here. We can just delete this. We don't need this anymore. Okay, one last thing, and this one is completely optional, so feel free to skip this if this is too confusing. But we have like this entire sequence that checks if something is walkable or not, and I think it's a good idea to put this into our own function, to create our own function that checks if something is walkable or not. At the very end, we're going to create a new function, function walkable. This function will accept two parameters, p and x, p and y, and then I'm going to go end. This is our own function. It's called walkable. It needs two numbers to function. And something we can do now is we can copy this code that we have here. I'm going to put it in here. Now we're going to replace new x with the p and x and p and y. The function will receive some numbers, and we're going to plug those numbers into mget. And then I can say the same thing that I have here, this if statement. I can put it in here. So if the tile is false, then we're going to return true. It is walkable. Otherwise, at the very end of the function, we're going to return false. So yes, this function will now check if something's walkable or not, and will just return true or false. So we can take advantage of this function right away. Instead of this very complicated thing, we're going to say if walkable new x new y equals true. Now, because an if statement already checks if something is true or false, we can actually leave out this equals true and use it like without any equation sign, if something is walkable or not. Let's save this, let's run this. And indeed, it works perfectly. We now have created our little collision detection function that will come in handy later as well. And this concludes level 1. We now have the most basic system to allow us to walk around on the map. This, of course, is not a full game yet. We can't leave the map. I mean, we can leave the map. We just disappear, right? We also can't interact with objects and so on and so on. But you can build a system like this out to become a full game. If you want to see how this works, I actually recommend a tutorial from a different channel for this. I recommend Dylan Bennett's top-down adventure tutorial. Dylan does things a little bit differently than I do, but the principles are the same. And he walks through a lot more of the steps that are required to turn something like this into a full game. And yes, this looks nowhere like Zelda. This is very choppy movement, obviously. But it was very easy and simple to set up, and it is more than enough for simple Sokoban-style puzzle games or simple adventures. Back in the days, we used to play games like Chip's Challenge for hours on end. That game had a movement system that looks exactly the same. Don't underestimate this. You can make a lot of game with a system like this. That being said, if this is too easy and you're ready, it's time to ascend to level 2. Fair warning, we are shifting gears here a little bit because I would love to explain every single step, but we will be here all day. I mean, it's called level 2 for a reason, right? Okay, so far we have the sprite of PP, it's moving around, it's turning around, it's firmly locked to the grid, and it makes those harsh jumps between positions. However, there is collision detection already, so that's really nice. We have tagged the tiles of the bush as not walkable, and the code responds to that and doesn't allow us to walk on top of them. Our goal for level 2 is to smooth out this entire transition. I want to have smooth transitions between the locations, and I want to add animations. However, we will still stay locked to the grid system because that makes collision detection so much easier. You will see later why. We don't even know how good we are feasting here. Alright, first of all, let us achieve the smooth movement between tiles. In order to pull this off, we need to split our update function in two different modes. In one mode, we're gonna wait and respond to button inputs. We're gonna call this idle mode. In the other mode, we're gonna move the character from one tile to another. Let's call this move mode. And once the character has moved to its destination tile, we're going to switch back to idle mode. This is a common setup in game development. This is called a state machine. It's when your code does two different things depending on a variable. In order to set up a state machine, we need a variable that controls which mode we're on. Let's create one called mode. Very creative. We're going to start out in idle, and don't forget the quotation marks. Now, this update function, we're going to rename this into check butts, because that's what we do. We check the buttons. What do you think that means? We will also create a new update function now, because the other one has been basically deleted. This update function will now look at which mode we are currently on and then trigger different functions as a result. So for example, if we are mode idle, then we're going to go check buts. Like this. Again, make sure the double equal sign is here because we're comparing whatever is inside the mode variable with this text idle. It's comparison, not assignment. So we now only respond to button presses when we're in idle mode. I'm going to save this, I'm going to run this, and it works the same way because we're always in idle mode. We're never leaving idle mode. In fact, let us print the mode on the screen just in case so we know what is happening. Print mode 887 like before in the draw function, so we see that we're always in idle mode, it never changes. Next, we need to react to button presses a little bit better. First of all, let us keep track if a button was pressed at all. I think it's a good idea to create a variable for this. I'm gonna go local press equals false. So this variable will be true if we press the button and false if we haven't pressed the button. Now actually use a new word here, local. Don't be afraid. If you put the word local in front of a variable definition, that makes this variable a local variable. A local variable is a variable that is a bit disposable. It kind of disappears after this function is finished. It's only available in this function. It's just a temporary little helper variable, not something that will remain over multiple functions and over multiple frames. If this is confusing, it doesn't really matter that much. In most cases, you can just leave out this local word and the code will work exactly the same. But you know, this is level 2, and I think it's a good practice to start thinking about the variables and what their purpose are. In this case, this is a perfect example. We just need to know if a button was pressed right now in this function. And indeed, new x and new y is also a local variable, could be a local variable, because we aren't actually using those variables outside of this function. Now here inside those if statements, I'm going to set press to true. And I'm going to do this with each one of those if statements. So there we go. So every time we press a button, we set this variable to true. And we need this because we want to switch to the walk mode only if we actually press a button. Technically, until now, we were walking to a new tile every single frame. We just didn't notice because it happened instantaneously. And most of the time we were walking just in place anyway. But now we are triggering a whole animation. And so we need to make sure that we do this only if a button was pressed. So we're going to take this entire if statement and we're going to put this inside another if statement. We're going to say if press equals true, or just like press then. Now these are two nested if statements, and something that's very important to also develop as a habit is to use indentation to mark whether an if statement is inside another if statement. Something that can easily happen is you can accidentally delete an end, and if you do that you will get an error. It's very difficult to track down this error. So what I want you to do is whenever something is inside an if statement or a loop, I want you to just like for every single line inside, I want to add a space at the beginning. This creates this nice little stairway pattern and it allows you to track visually if you closed all of the if statements that you opened. Anyway, let's save this and do a final test before we break things. Seems to be going well. Let's burn it all down. First, instead of approving the movement right away, let us delete those two lines and instead set the mode to move. Now above in the update function, we're going to create a second if statement, else if mode equals move then. Now this is a bit weird. We are using this else if now. This else if thing is a way to merge two if statements together. So now whatever is happening here gets only checked if this first statement wasn't true. So it's either idle or move. Not really that important here, but it will be important later down the line. When we're in move mode, I want to call a function called movePlayer. Now, you might notice that this function doesn't exist yet, so let's create it. Function movePlayer. All right, so now we thoroughly broke things. When I save this and run this, I press a button. We are now in move mode and we never leave move mode. Nothing responds to button presses anymore. We are now locked out. So the idea now is that we're supposed to slowly move the sprite across the screen when we are in move mode. And in order to pull off such an animation, we need to keep track of how fast the sprite is supposed to be moving. So at the beginning of checkbuts here, let us create two new variables, player speed x, player speed y. We start at 0 because we are idle, and when we're idle, we're not supposed to be moving. Also, these are specifically not local variables because these variables are something that the move player function needs to access as well. Alright, so now in the individual button presses, we need to change the speed of the character. And this is very similar to the way we change the position of the sprite, just a little bit slower. PSX equals -1 if we're moving left, +1 if we're moving right, PSY is -1 when we're moving up, and PSY is +1 when we're moving down. By the way, this 1 is not just made up here. That's actually the speed at which PP is moving in Link's Awakening. PP is always moving at 1 pixel per frame. So now that we have set up a speed for our sprite, we can actually start animating things. Here in the move player function, we write the following. PX, the player position, equals PX plus PSX. And the same thing for Y as well. PY equals PY plus PSY. Now at this point I want to show you a little trick. There's a quicker way to write this. We can also write PX plus equals PSX. This line is the same thing as this line, and I'm going to prefer using this line because it's a little bit shorter. So we can rewrite this into something like this for PY and PX. Let's save this, let's run this, and we press a button, and hey, we're moving! Goodbye forever. Alright, so we're moving, but we need to now find out when to stop moving. One easy way to pull this off is to just keep track how many pixels you've moved so far and just switch back to idle mode when you moved the certain amount of pixels. In our case, we always want to be moving 16 pixels, so let's just make sure that after we moved 16 pixels, we stop. In the checkbox function at the very bottom here, when we set it to move mode, let's set up a new variable called distance and set it to 16. And then up here in the move player function, let us set dist minus equal 1. This is the same writing as we had above here. We're just subtracting 1 from the dist variable every single frame. And then we're just going to check if we hit 0. So if dist is smaller or equal 0, it could be smaller, I guess, then we're just going to set mode to idle. Bam. We save this, we run this, and hey, we're moving! Virtual insanity, bam, it works. Now let's tweak some things. I want to show you that if you keep the button pressed, you see a little bit of a stutter. Why is that? Well, this is because we are using the BTNP function. The BTNP function is only true the first frame that you press a button. If you keep that button pressed, it will no longer be true. Now, at some point, it will start repeating, but triggers only occasionally. That's why you get this stutter. There is a second function to check if a button is pressed that works continuously, and that is the BTN without the P. So let's switch those BTNPs with just BTNs. On a previous level, it was better to use BTNP because when we press the button, we want to move a whole space. So we actually wanted to have a bit of a break after we press the button. Now that break is a little bit unwanted because we already have the animation, so we don't need that extra break. Now let's save and run this, and this works a lot better. Now if you are very careful and if you watch it very closely, you will see that there is still like 1 frame of stutter in here. Let's get rid of that. The trick that we can use here is we can actually call our first instance of move player down here when we change the mode. So on this very same frame that we press the button, we already moved the first pixel. This removes that little stutter that we have, like this. A lot better now. A lot better. Another problem that we have is that we can now move diagonally, and we're gonna do that in a later level, but for this level I don't want to be moving diagonally. This causes a lot of problems. Let's get rid of that. And the way to do this is, I already teased this, we're gonna link all of those button statements together to else if statements. So now only one of those button statements can trigger every frame. So if you press 2 buttons at the same time, only one of those buttons will get responded to, usually the one that is further up in this list. I'm going to save this, I'm going to run this, and now I cannot walk diagonal anymore. A bit sad, but it's for the best. So far so good. As much as I love Jamiroquai, we need to add a bit of an animation here, I think. Now, reviewing a footage of Link's Awakening reveals that the animation is pretty slow actually. Each individual frame of the animation is shown for 8 frames, for 8 game frames. So we need 3 things. We need to have a counter that tracks how many frames we've shown a single sprite of the animation. We need to have a second variable that tracks which sprite of the animation we are currently showing. And we need to somehow remember which sprite numbers belong to which animation. So in the init function, we're going to create player animation timer. That's going to be the variable that counts the number of frames we've shown a single sprite. We're going to start at 0. Then we also need to save pani frame. This keeps track of which frame of an animation we're showing. Our animations are very short, just 2 frames. I'm going to start at the first frame. And then we need to keep track which sprites belong to an animation. We're going to have one animation for now. We're going to call this pani, player animation. And we're going to save this in a so-called array or table. And we do this with a curly bracket. Curly bracket 0, 2, close curly bracket. So this is an array or a table. This is 2 numbers or even more numbers stored in a single variable, and we can cycle through those numbers. I'm going to show you in a second how this works. What you need to know is that this is a sequence of numbers 0 and 2, and this corresponds to this sprite. The top left corner of that sprite is 0, and this sprite, the top left corner of that sprite, is 2. That's the downwards working animation. Now we need to do an animation when we're moving the player. Let's do this here. So in here, we're going to advance the player animation timer. We're going to go plus equals 1. And if the player animation timer, if that reaches is greater or equals 8, then it's time to advance the frame. How do we advance the frame? Well, it's this here, pani frame. Pani frame plus equals 1. We're going to add 1 to the animation frame. Now, there's just 2 frames. It's not a lot of animation. So if we're above 2, we need to cycle back to 1. So we're going to go if pani frame is greater than 2, then pani frame equals 1. And I know this is a bit clunky. We have such short animation. It doesn't make sense to create all these if statements. There's easy ways of doing this. But I want to set up a system that can potentially handle longer animations. And I think for that, this is the correct way to go. Now, there's lots of variables happening here. Let's draw them to the screen. Let's debug this to make sure that we understand what is happening. So I'm going to draw the player animation timer to the screen a little bit further down at Y position 16. And also I'm going to draw pani frame even further down at position 24. I'm going to save this, I'm going to run this, and you can see, I already spotted a certain problem. The player animation timer doesn't reset to 0. We forgot about this. So let's, inside the if statement here in the move player function, when we reach 8, we want to reset down to 0. Let's save this, let's run this, and as you can see now the numbers are advancing correctly. We count up to 8 and we return down to 0. It happens very fast. And you can see that the second number is also alternating between 1 and 2. These are the animation frames. All right, so the numbers under the hood are working correctly. Now let's plug them in to actually show us the correct sprite. Here in a draw function, so far we're using PSPR to draw the player sprite to the screen. Now we want to grab the player sprite number from our animation table. So we're going to take the pani in here and we're going to plug this in. Now, in order to access one of those 2 numbers, what we need to do is we need to do a square bracket. And then we need to put inside the square bracket the number of the entry that we're interested in. So if you put number 1, it will show us the sprite number 1, which is 0 in this case. If we want to have the second entry, we're going to say 2, and that will actually correspond accidentally to also a 2 in this table. And you can see the shield is now a little bit angled, right? And the important thing about tables is that this number is blue, and blue means that this could be also driven by a variable. And that is exactly why we have pani frame. So we put pani frame in the square brackets, and now the pani frame will cycle between those 2 entries in our table. So if you run this, you can see, yes, we're walking, the animation is cycling perfectly, but alas, we're only looking down. So how do we turn around? Well, we need to create separate tables for all of the different animations that we have in the game. We have 4 animations, so let's create 4 tables. In the init function, I say walk ani L for walk animation left, walk animation right, walk animation up, and walk animation down. Put little comments in here just so we know what is what. And now I need to find the corresponding numbers. So we know already that down is 0.2. That's already what we have. In fact, we can start the player animation as this. We're going to just assign the player animation to this table, right? Now for the up, we need 12 and 14. For left, we need 4 and 6. And for right, we need 8 and 10. So now when we press a button, we just need to swap out our animation table. So instead of PSPR, that was just a single sprite that we changed, PANI table, I'm going to set this to walk ani L. So the left walking animation when we press the left button, the right walking animation when we press the right button, up walking animation when you press the up button, and the down walking animation when we press the down button. We're going to save this, we're going to run this, and beautiful. We are walking and there's a beautiful animation playing. Is there something greater in the world? I don't think so. Yeah, I'm serious. This is looking really great. You can see that the game really comes alive and you can see how the animation really sells the idea this is a character that's walking around and turning around. Wonderful. In fact, I want to tweak one little detail. There's one little thing that you don't quite see consciously, but maybe your brain picks it up. There's currently a little bit of delay. When you press a button for a very short amount of time, the sprite won't actually change. It will take about 8 frames until we see a new frame of the animation. For 8 frames, we're going to have a micro virtual insanity. And this is because when we press a button, the counter starts counting up and it takes 8 frames until it reaches number 8. And only then the animation will switch to a new frame, to a new sprite. Until then, we're going to see the old sprite that we saw when the character was standing still. I want to see a new sprite right away when I press the button. This will make things seem a little bit more responsive. Here's how we do this. So in the checkbuts function, when we press the button, instead of the and, we can do an else and then end. So if we are not pressing a button, I want to actually reset the animation to a number. Pani T, player animation timer, we're going to set it to 7. So just before we're about to switch to a new frame. This is going to be our default at which the animation timer will sit. So when we press a button, it will immediately switch to the next animation frame. And also while we're here, I'm going to set pani frame. I'm going to set this to 1. So the character always returns to frame number 1. Not relevant right now, but it might be relevant in the future. All right, let's save this, let's run this, and yeah, we now get more of an immediate response when we press the button. Again, it's not very blatantly obvious, but it makes things just a little bit more responsive. And here we are. This is a fantastic setup for a lot of retro 2D top-down games. If you go back and take a closer look at a lot of JRPGs from the NES, Super NES, Game Boy Advance era, they will look exactly like this. All of the 2D Final Fantasies, even up to Final Fantasy VI, look like this. All of the 2D Pokemon games, even the ones on the GBA, also look like this. This is a good setup and it's easy to see why. It looks nice and responsive, there's some beautiful animation happening, and it was very easy to set up. Look at this. Our collision code is like what? 5 lines? That's insane. We can even simplify this. Look at this. Something like this, right? It's just 2 lines of code for the entire collision detection. Does it work? Yeah, it still works. It's fine. Oh, and by the way, while we're cleaning up, let us get rid of PSPR. We don't need that variable anymore. So yes, this gives a lot of bang for your buck, and for everybody out there who wants to just recreate the look and feel of old JRPGs, this is all you need. But obviously there are still drawbacks here as well. We are still locked to this very coarse 16x16 grid, and we don't have that kind of fine control over our positioning. This is fine for like RPGs like Final Fantasy or Pokemon, where you don't have to like, avoid projectiles. Those games don't have any action elements. For an action adventure like Zelda, you might need a bit of a finer control. Unless there is another. One of my favorite games on the Game Boy ever is this. This is Final Fantasy Adventure, also known as Mystic Quest for the Game Boy. Also known as Seiken Densetsu Final Fantasy Gaiden. Also known as the prequel to Secret of Mana. Also the game that Sword of Mana and Adventures of Mana was based on. And you might be thinking, this game got 2 remakes? This game got 3 remakes. We don't talk about the flip phone version, that's a limited loss media. Yes, this game is quite special. And one of the reasons why I think it's so special is that it is an action adventure like Zelda, but it still has grid-locked movement like here. But they used a really nice trick to make this a little bit more responsive. You see right now, each step moves us 16 pixels, a full meta tile. That's a big step, but each meta tile is made out of individual smaller 8x8 tiles. And those smaller tiles make a much finer grid. So with just a few easy tweaks, we can be actually moving in this finer grid. Let me show you how. We just go to the check butts function right here, and instead of 16, we change this to 8. It's that easy. And also here, when you have the dist, where we set the distance, we also need to change it down to 8 because we're moving less now. And that's all we need. Now we have a lot finer control over our positioning, and the player character is a lot more responsive now. Now there's something that is broke, and that is the collision detection. If I walk up, I cannot walk over this bush, but I can partially overlap these bushes on this side, and I can also partially overlap the bushes coming from the top. Essentially what happened now is our collision box became smaller all of a sudden, and it's now confined to the top left corner of our player sprite. This is because we are working now on a finer grid, and one single tile check doesn't cover the entire player sprite anymore. But that's not that big of a problem, we just need to check a few more tiles when doing collision detection. Down here in the check butts function, down here where we're checking if a tile is walkable, we need to check just 2 tiles instead of 1 tile. I'm going to do this like this. I'm going to go and I'm going to copy this over here. So now we're checking for 2 tiles. I'm going to put a line break in here so we can see it all on the screen at the same time. And now we need to offset those tiles. The top left corner, we don't actually care that much. We want to move this maybe 8 pixels down. And then for the lower walkable check, we need to do +8 here and +8 here. Something like this. Let me show you how this looks. So now we can walk around. We can walk in front of the bush, so to speak. We are slightly overlapping the bush, but that looks good. That is what we want. And coming from the top, we're not overlapping. Coming from the sides, we're also not overlapping anymore. We essentially change the collision box of our character to be the bottom half of the sprite. But again, that's actually what we want. We get that kind of spatial effect where the bush seems to be behind our player sprite. This is a very cool tweak, and this is exactly how Final Fantasy Adventure works. And it's great. It gives you just this little bit more control to make it viable for an action adventure title. But collision detection is still so easy to pull off. I'm not gonna lie, in terms of complexity and what you get for it, this is probably one of my sweet spots for this entire video. This is pretty good. But the point of this video is not to end at a happy medium. We need to push on straight into level 3. So we begin at a pretty good spot. We have set up a state machine that alternates between moving and responding to button inputs. We are still locked to the grid, but it's a very fine grid, so we have good positioning control right now. And since we operate on the grid, the collision detection is really nice. We can even walk in front of an object, so to speak, to create that kind of perspective view. We have a great solution, and we are about to set it all on fire. Because while convincing, this is not actually Zelda. There are 2 things that make Zelda different from this. First of all, in real Zelda, PP is not locked to the grid. They have pixel perfect movement. In addition, they can also walk diagonally. This is great for precise action gameplay, but as we will see, it will come at a cost of complexity. Now heed my warning, I have seen many devs underestimate this and fail. They developed too greedily and too deep, and they awoke something in the darkness. And now we shall face it. First, let us get rid of the debug stuff. Let's remove those print statements. Second of all, let's tear down this state machine. A true Zelda game responds to button presses and animates the character at the same time. Like this. Now here in the move player function, I want to split things a little bit. First of all, we don't need this disk check anymore. And this part, this is all about animation. I want to put this into its own function. Function AniPlayer. This leaves our move player function with just those 2 lines. In the checkbox function, we can just delete this entire collision detection. That will just work differently now. And we can also delete the new X and new Y. We are no longer working on the grid, so these are superfluous. We also delete those from the if statements on the button presses. Those are done so now. And still in the checkbox function, I actually want to call AniPlayer and MovePlayer here at the very bottom. Like so. Let's save this, let's run this, and hey, it just works. We're walking around, but alas, there is no collision detection. But hey, we have pixel precise movement. That wasn't so hard, was it? Okay, yes, sure, our character is also constantly walking, but we're going to deal with that in a second as well. But how do we do collision detection now that our sprite is no longer locked to the grid? Well, we are no longer locked to the grid anymore, but we can still check which tile is underneath a given pixel on the screen, right? So we can still check which tiles our sprite overlap. We just need to be maybe a little bit more specific and more precise about which pixels we're checking. A good solution is to sample all 4 corners of our sprite. If we are moving the sprite and one of the corners starts overlapping something that is not walkable, we should stop the movement. Before we implement this, let's set up a little visualization of this. In the draw function, I want to set up a table of points. And inside this table, we're going to have smaller tables, and those tables will be X and Y coordinates of points. Something like this. Now, instead of 0 and 0, I want to actually take things that are relative to the player's position, so Px and Py. So Px and Py would be the top left corner, Px plus 15 would be the top right corner, Px and Py plus 15 would be the bottom left corner, and Px plus 15, Py plus 15 will be the bottom right corner. Now you might be wondering, if the sprite is 16 pixels wide, why are we writing 15 in here? We want to sample the last pixel in this sprite. But if we add 16, that's actually not the last pixel in this sprite, that's the first pixel in the next sprite. You can see this in the pixel editor here. The last pixel in the sprite, down the bottom left corner, you see it's 15, 15. 16, 16 is the next sprite over, it's here. So now that we set up this list of points, let's draw those points to the screen. There's a nice loop that you can use for this, for P in all points, do end. This is also a very common solution. The code inside this loop will get executed, will get repeated for every entry in this big points table. And conveniently, every time it gets repeated, P will get turned, will get assigned to one of the entries inside this point table. So P will cycle through all of those points that we have in this table. So now we can just draw those points with a pset command that will just draw a single pixel at a certain coordinate, and we're going to get this coordinate from the P, like this. X coordinate from the first entry, Y coordinate from the second entry. And then we have to pick a color. Let's pick 7, a white color. Let's save this and run this, and you can see there are our sample pixels. These are the pixels that we want to check if they're overlapping a sprite that is walkable or not. And the beauty of it is that we can still use the same code that we used before, this walkable function. It's the same thing. So we do something like if walkable P1, P2, then we draw a white pixel. Otherwise, we draw also a point, but this time we're going to draw this in the red color. This is just for debugging purposes. Let's save this and run this. And beautiful, our points light up like a Christmas tree. That's fantastic. Now all that we need to do is to make those points drive our collision detection. Now, as we Germans say, let's make nails with heads right away. Let's put all of this stuff right away into its own dedicated function called checkMove. The job of this function is to check if the player can be moved that many pixels to the side and upwards. It will perform the move, it will check the collision, and if there's a collision, it will say sorry. It will return false. If there was no collision, it will return true. So let's fill this with wonderful stuff. We take this code, we're going to actually get this out of the draw function and put it in the check move function. Now here, this part, we're going to copy out and put it in here as well, but just copy for now. Okay, so now let's adjust this code so it works with a new function. First of all, let's create a set of variables that track the coordinates of where the player would be if we perform this move. Local new x equals px plus dx. We take how much we're supposed to move the character, we apply it to the position of the character and save the result in a local variable. We're going to do the same thing with y, like so. And now we're going to take this and we're going to plug this into our point generation thing, like so. Beautiful. Now down here, when we make things walkable or not walkable, we are actually not interested in drawing pixels anymore. We just want to make sure that if it is not walkable, we can do it like this, for example, not walkable, then we can return false. And at the end of the function, we return true if all the checks have been performed and there was no problem. Like this. Now, I have to say, I actually like the debugging that we did here when we saw the points lighting up red when they collided with something. So let's keep this around, but this time around, the colors, it's not something that I want to calculate here in draw function. I want to actually calculate the colors down in a collision detection function, and I want to save the color in the point table. So something like this, we're going to say the third number in the table is going to be the color, and we can remove the rest here. So it's just drawing a pixel that is saved in the table at this location 1 and 2 with this color 3. Now this color 3 doesn't exist yet, so let's make it exist. So the last entry in the table, the third entry, is going to be 7. That's going to be the white color. And down here, when we detect a collision, we're going to set the third entry in that table for this point. We're going to set it to red. P3 equals 8, like this. That should be our function. Now let us make this function actually drive our collision. So up here in the checkbox function, at the very end, after we press the button, we can go if check move PSX PSY, then move player and animate player. Let's save this, let's run this, and we can walk around and we can collide with stuff. You can see which point issued the collision detection. The movement has been cancelled, so to speak. That's perfect. And everything is peachy. But wait a minute. What is happening here? It's so difficult to enter those gaps. What is going on? It's almost impossible to enter those gaps. Look at this. I cannot enter this. What is happening? Why is this happening? I get stuck on the geometry all the time. Why is this happening? Yep. That's what I was talking about, and it's even worse than you think. You might be thinking, hey, maybe we just made the hitbox a little bit too big, but that's not true. The hitbox is the same as it was before. When we were walking through those gaps before, we were exactly the same position that the game asks us to be now. It's the other way around. By giving us full freedom of movement, we made those gaps just so much harder to hit. The game doesn't align the sprite for us anymore along the grid. We have to do it manually, and it's tight. We didn't realize how much we were feasting. This is a wicked problem, and it's a problem that I see a lot of devs struggle with. This is something I struggle with as well. This is especially hard because unlike previous problems, this doesn't have one single solution. There's a lot of tiny little things that we can add to make those gaps easier to hit. But know this, wrestling with this is the true cost of making a Zelda game like this. Things are about to get messy. On the other hand, this is actually the real reason behind this video. I wanted to analyze the footage down to the pixel to see how the legendary devs of the past approach this issue. And I have some knowledge to share, so let's dig in. First things first, yes, obviously the hitbox has to be smaller. Duh. I did some experiments in Link's Awakening. I came up with these numbers. New px plus 4 is a good number. This lowered to 11. This is also plus 6 here. This is plus 4. This stays at 15. This is 11 and 15. Let's save, let's run this. So you see now the collision box is much smaller. We have actually some wiggle room between the tiles, and this makes it easier to hit those gaps. That's a lot nicer for sure. But also you see we still get weirdly stuck on the geometry. It's like it feels sticky. It doesn't feel nice. Ugh. Sadly, our job is not done. But since the collision detection broadly works, let us first finish up the other features that a Zelda game needs. We need diagonal movement. All we need to do is to disengage those if statements from each other. We no longer need this huge else if stack. We now have to turn them back into individual if statements. So now multiple button presses can be processed at one frame, and this allows us to walk diagonally. But if you look closely, like this looks weird. It looks like I'm speeding up when I'm walking diagonally. Walking diagonally is faster. How is that the case? Yes, this is once again a common issue and something I talked about in great lengths in my shmup videos. When you press two buttons at the same time, you move sideways and upwards at the same time, and those speeds add up, so you end up walking faster in total. This is essentially vector math. The speeds add up to a vector of a greater magnitude than the initial speeds. To tackle this, we need to do something called normalize. We have to normalize our diagonals. This sounds complicated, but it's actually not that hard. Actually, you just need to multiply the speed with 0.7 when you're walking diagonally. And we start implementing this by checking if we are actually walking diagonally. Now, currently we have like this variable here that checks if a button was pressed at all. Let's change it so it counts how many buttons we pressed. So we start at 0, and here in the if statements we go plus equals 1. So we count how many buttons were pressed. Like this and like this. Now here we're going to do the same thing we did before. We're going to wrap this in an if statement. We're going to say if press is greater than 0. So if a button was pressed, then we're going to check the move, we're going to move the player, and we're going to animate the player, and so forth. And now inside here we can check if we are going diagonal. So if press is greater or equals 2. And here's where we normalize. So we're just going to go PSY equals PSY multiplied by 0.7. And the same thing with X as well. Overall, both directions will be slower, but if we add them together, it will even out to be 1 again. Let's save this, let's run this. And this looks good. This looks as if we were walking at the same speed. This is great. But oh no, why are we shaking like this? What is happening here? Why is this so jittery and weird? Oh. Yeah. That's another one of those common issues. It's one issue after another. I told you. This is something I like to call cobblestoning, and it's a bit of a weird issue that comes up especially in Pico-8. You see, by changing the speed to 0.7, we create a situation where sometimes PP's position on the screen can have a comma value. It can be between the pixels, so to speak. Sometimes we also use the term subpixel position. And let me show you why this is an issue. Let's draw a diagonal line through a grid and color in all of the squares that we touched. If we draw that diagonal line perfectly through the corners of the grid, it will create this neat stair pattern. That's what we want. That's what we had until now. Now, if you move that line just a little bit off center, if you don't hit the diagonals perfectly, you will end up with a jagged stair pattern. This is the path that PP is sometimes now following when he has some kind of weird subpixel value. Once again, this is a problem I see a lot of devs hit quite frequently. And actually, I think also a lot of commercial games actually have this issue. It's just in Pico-8 the pixels are so huge, it's very apparent when this happens. I have been struggling with this as well, but luckily I've developed a solution in the advanced shmup tutorial. The trick is to reduce the player's position to an integer number to remove the subpixels every time you change direction. That is all we need to do. And here's how to implement this. So inside the checkbuts function, we need to recognize when a different set of buttons have been pressed than before. Now we can actually take advantage of the btn function. Right now we're using the btn function with something in the parentheses. But if you use it without something in the parentheses, it will actually return a single number that encodes all of the button presses at a given frame. They're encoded as bits in this number. We can save this number, we can advance to the next frame, and we compare the old number with a new number that we get. If the numbers don't match, we know that some button has been pressed or depressed or something has changed. In the init function, we're going to create a variable called last btn, and we're going to set it to 0. Now at the very bottom of checkbuts, as the very last thing that we do, we're going to go last btn equals btn without anything in the parentheses. And then a little bit higher up, perhaps here, let me write normalize, then maybe here we can do anti-cobblestone. If last btn is not equals btn, so a button has been pressed or depressed, something has changed from the last frame. Px equals floor px. Strip out the comma value, the stuff after the comma, from our positions. Like this. Let's save this, let's run this. And you see there is no jittering anymore. We have smooth diagonals now. This is what we wanted. This is good. So many pitfalls to solve. Oh, this is horrible. Speaking of which, let's look back at the collision detection. Now that we have diagonals, now suddenly collision detection is even worse. Look, when I'm walking diagonally, I get like hung up on the bushes. I cannot just continue walking diagonally. I cannot slide off the bushes. This is bad, and it hints at a different lens through which we can look at this problem. The problem isn't really with the collision detection. The problem is actually what happens when you collide. All of this collision tends to stop us dead in our tracks at a moment where we actually just want to keep moving. And I want you to keep this in mind. This should be maybe like a guiding principle. Whenever we do some collision detection right now, we should seek ways of how we can make the player keep moving anyway. And this is something we're going to deal in next level, but as the very last thing for this level, I want to create a situation where we can slide along the wall. Let's call this the diagonal slide. So this situation happens when there was a collision detection. So this part here in the checkbox function, where we do the collision detection, we need to pull this apart a little bit. We need to check if there was a collision and they maybe react to it before we move or don't move. So let's do something like this. Let's go local no call equals check move. And then if no call, meaning no collision, if there was no collision, then we animate and remove. We just pull this apart into two-step process, so now we can put something in between there. So for example, if no call equals false and press equals 2, then, so if there is a collision and we are walking diagonally, then we might want to attempt this wall slide, this diagonal slide. So what should we do in order to slide along a wall? Well, one of the things we can do now, instead of going diagonal, we can just try walking straight and see if this results in a collision. So we're gonna do something like if check move this, and now we can zero out one of the movement directions. Remember, we're walking diagonally, so both of these variables have numbers stored in them. We're just going to zero out one of them, which result us going either horizontally or vertically. So if this is fine, then this is actually a good way to walk. So let's just change the movement speed to whatever we had. So we go PSY equals 0, and we're going to green flag the collision. We're going to say no call equals true. Otherwise, and let's zero out the other movement directions. So else if 0 PSY, then, and we do the same thing just with the other variable, we go PSX equals 0 and no call equals true. Now also down here, I just noticed, we move the player, we animate the player if there was no collision. Actually, we always want to animate the player. We only move the player if there was no collision, but if we press the button and there was a collision, we want to still, we want PP to be struggling against the wall. Let's save this, let's run this. And so now we can walk. We can, now when we walk against the wall, the animation keeps running. But now does the diagonal slide work? It works, it works. We can now move along the wall if we walk diagonally. That's nice. This allows us to keep moving if we hit something while walking diagonally. Now, PP is a little bit slower when doing the wall slide. I think this is kind of fine. It feels a little bit like there's a bit of a friction between the wall and the character. If you want PP to be walking at the same speed when doing the wall slide, there's a way to undo this. We basically have to undo the normalizing. And here's how we do this. We go PSX equals PSX divided by 0.7. Here above here, to do the normalization, we multiply it by 0.7 and we undo this by dividing by 0.7 for the remaining speed variable. And down here, we do this for the other one. Save this, run this, and now we are moving faster when we're wall sliding. That's what we wanted. Beautiful. Wait, there's one more thing. At the end of the last level, we added something to make the animation a little bit more responsive. We deleted this. So what you need to do at the end, you need to add this little bit in here. an else instead of the end, and then p any t, we're going to reset that to 7 and the frame to 1. This part is very important, especially in this level. So now we're complete. Look at us. We made it through level 3, and what it cost us? A lot. But I think this is pretty good movement, all things considered. We fell into all those pitfalls, but we conquered most of them. The collision detection is still not ideal. You still sometimes gets like, look at this. It still gets sometimes stuck on the corners. It doesn't quite feel nice. But as I said, this is a problem that never gets fully conquered. Perhaps this is good enough. If you want to make a Zelda-like adventure, this is a perfectly acceptable foundation. And yet, this is not the true Zelda yet. There is still a couple of things we can do. But before we do, you have one last opportunity to save yourself. As I said, this is a wicked problem, and as we keep adding little features to make this better, we keep adding complexity and we keep adding breaking points. And we're also getting diminishing returns. So maybe this is actually as good as it gets. Fly, you fools. Where are we? We have a freely moving character. They have a 4-point collision box. There are collision checks with tiles. This is nice. We have diagonal movement. We can slide off the collision boxes when we hit them when walking diagonally. This is nice. We normalize the diagonals. We fix stuff like cobblestoning. Everything is peachy. Link's Awakening has all of this and just a tiny little bit more. Now, actually, I have to admit, I haven't actually looked at the real Link's Awakening code. And if there's any people watching this who are into like Game Boy ROM hacking, please get in touch with me. I want to know what the real code underneath actually is. But looking at the footage and analyzing, things pixel by pixel, frame by frame, I figured there's 2 more things that Link's Awakening does that we can try. First is dynamic hitboxes, and the other one is corner slippage. So dynamic hitboxes just means that the environment hitboxes that our players have change depending on which direction we're currently moving. So when moving horizontally, the hitbox actually narrows vertically to allow you to avoid obstacles that are in your way. Obstacles that are not perfectly in front of you, but just like, off to the side. On this footage, you can see how approaching an obstacle from the side lets PP penetrate deeper into the bush. Let me rephrase this sentence. Approaching an obstacle from the side allows for a bigger overlap between the player sprite and the obstacle. This suggests to me that the hitboxes have different dimensions depending on which direction you're moving in. Let's implement that. So we generate our collision box, our sample points. I called it a box, it's just 4 points, right? We generate them here. And they are based off of these numbers here, right? So basically, if you want to change the shape, the size of the box, we have to exchange all of those 8 numbers. Let's make it so that these numbers are driven by an array, by a table. Now let's, here in the init function, let's create something like call equals, and then let's take those numbers that we had before. I'm just going to paste them in here because I already know what those numbers are. And now those numbers we can just put back into our point generation system. So we're just going to go call, this is the first number, this is the second number, and so forth. And this is the 8th number. Let's save this and let's run this and see if this works. The collision box, the sample points still look the same. So we just recreated things, but now those points are driven by an array, by a table. So now all we need to do is, just like with the animations, we need to create different types of tables for the different directions that we're moving in. I'm not going to speed things up because this is a bit of a menial process, but I figured from looking at the footage, I figured out these numbers are kind of correct. And then we're going to set the collision box that is default to call D, which is the collision box when going down. Now, as you can see, these are 2 collision boxes, basically horizontal collision box and vertical collision box. We're kind of repeating one collision box, but we're going to see why in a second. Let's first trigger those boxes when we press the button. So we're going to go call equals call left, right, up, down. We save this, we run this, and now you can see the collision box changes shape. It elongates along the direction that we're traveling. This is great. So now we can approach an obstacle from this side and we can get a lot closer than we otherwise would be. Oh no. Yep, this is the problem. You see, because we have those collision points in the back, when we create a little bit more overlap by approaching the object from the side, we are so deep inside the obstacle, the collision boxes on the back prevent us from walking straight away from it. The solution is simple. We actually, because we have 4 directions and we have a collision box for each one of the directions, we can actually get rid of the points in the back. They're not doing anything anymore. Indeed, so let us just do a collision box, which is no longer a box, it's just a line with 2 points in the front. This also means that we need to simplify our collision box here, something like this, 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 and this. I think this is right. Let's try this. Nope, this is not quite right. I've been too hasty. Here are the correct numbers. I've pasted them in. Let's see if this works. Yes, now the points are always in the front and they're checking if we have collision. And now if we approach an obstacle from the side, we create this extra overlap, we can actually walk away from it. This is what we wanted. Diagonal movements also works. This is good. I am a little bit concerned that sometimes when walking diagonally, you see how in the back we get like, when we slide off, we get a lot of overlap on the back, and I think this is because there is no collision box in the back anymore, so we walk to the side very early. That's something I would definitely pay attention to. If this was a real game, I would figure this out in playtesting if this looks weird or not, depending on the situations that we find ourselves in. And despite all of this, we still get sometimes hung up on the edges. It feels like it should be maybe able to walk here. Why is I'm still getting stuck and hung up on those corners? It's time to deploy the final trick. Going back to the footage I recorded of Zelda, if you look closely, you will see that sometimes people will sort of slide off the corner. If he catches the corner at the very edge, he will snap a few pixels to the side so we can walk past the obstacle. This is a very cool effect and makes it so much easier to avoid getting caught. And other Zelda games have this as well. In A Link to the Past, there's even like this smooth transition. It feels a little bit as if all of the obstacles have rounded off corners or if they're slippery. This corner slip effect is a little bit harsher in Link's Awakening, but it's still pretty good. How do we recreate this? I'm gonna be a bit honest here. I'm not exactly sure if I have the best solution, but here's what I got. For simplicity's sake, let's just apply this effect only when walking straight. We're not gonna care about this effect when walking diagonally. We already have the diagonal slip for diagonal walking. This is just for walking straight. So inside the collision detection, let's go back to here where the diagonal slide. So we're gonna say like, so if there was a collision and we pressed one button, then. And here is where we're gonna do our corner slip. Otherwise, else if, this is gonna be our diagonal stuff. Now let me fix the ends and do the indentation like this. Diagonal slide goes in here. And this is going to be the corner slip. So all of this gets triggered when there was a collision. And if one button was pressed, we do the corner slip. If 2 buttons were pressed, we're going to try the diagonal slide. We have kind of like disentanglement or keep moving solutions for both situations. Now, on doing the corner slip, I was actually thinking of doing some kind of algorithm that, checks where the next edge is, calculates the distance somehow. But it gets really complex because if you think about it, we have to do it in both directions and it has to work for both directions. So we have to cover all those different cases. So in the end, I decided a brute force approach might be the simplest one. The collision checks we're doing are computationally super simple, so we can easily afford making a whole bunch of those in a single frame. It shouldn't be a problem to just move the collision box a couple of times to see if we find a free space. So let's define 2 local variables called SLP slip X and slip Y. This is how much we're going to nudge around the box to find a free space. Now these numbers are wrong, but for now let's just move on. Let's create a simple for next loop. For I equals 1, 2, 3 do. So this loop will check different positions. First it will check 1 pixel away, then 2 pixels away, then 3 pixels away. It will try to find a position to the side that is perhaps free. And so let's calculate the new position. So let's go local SLP dx equals PSX plus SLP x multiplied by I. Same thing with Y, like so. So now let's check if we found a free space. We're gonna go if check move SLP dx, SLP dy. Then if we found a free space, that's great. Let's just do this and green light this collision. psx equals slpdx, psy equals slpdy, and no call equals true. Oh, and by the way, I just found an error here. That's going to be, we forgot the then here. There's a problem here. We forgot to change the x to the y. Let's run this again. Okay, so you see we get the slippage. We get the slippage here on the right edge of the bush. That's what we want. This is what we were looking for. This is good. Maybe it's a little bit too far away, but otherwise I'm good. Now this doesn't work on this, and obviously it doesn't work vertically at all. So now let's try to work this in the other direction, on the other edge of the bush. Making it work on the other edge of the bush requires us to repeat this process, but in a negative dimension. We have to subtract instead of adding. Here, instead of adding, we need to subtract. And there's multiple ways of doing this, but I kind of don't want to give up this for next loop, because it's kind of nice that we can change the strength of the effect by just changing this single number. If we want the slippage to be more intense, we can increase this number, right? That's nice. I want to keep this. But that requires us to create a bit of a cursed solution. Let me show you. So I will do a repeat loop. Repeat, and down here until. And we're going to put this entire for next loop inside this repeat loop. Until is when we stop doing the loop, and until, one of the conditions for stopping the loop is going to be no call. If we found a no collision solution, then that's great, then we are finished. But now the part where we go in both directions. So we're going to have a new local variable called j, and we're going to start it as positive. And then we're going to multiply the I with the j down here. So on the first loop, that's going to be just multiplied by 1. It will do nothing. But as when we finish with the loop, we're going to do j minus equal 2. So it will change from 1 to minus 1. And then the loop repeats. And so now we're multiplying with minus 1. So we now go in another direction. And then we're just going to go or j is smaller than minus 1. So if we're about to repeat this loop for the third time, we abandon. We haven't found a good spot. Save, run, and let's try this. And here we get a slippage here, we get a slippage here. The slippage is a little bit too much. Now you see sometimes the slippage is a little bit too extreme. And I know you see how we slipped very far in this time around. And there is one reason for this, and that's a little bit of a stupid mistake. Here I need to do a break. When we found our first opportunity to do the slippage, the very first opportunity we need to break this for loop and immediately exit out. We found our first opportunity. That's going to be the closest one. That's the one that we want to accept. If we continue this loop, we're going to continue finding more opportunities, and those will be further away. Let's save this, let's run this. And yes, this looks correct. Now we get slippage from this side, we get the slippage from this side. This is nice. Now this is just vertically. Let's also make it horizontally. This is all about tweaking those variables up here, which I told you were the wrong ones. So essentially this works. The slippage needs to occur in the direction that we're not actually moving in. So we need to find which of the directions that we're traveling in is 0, and we need to set the slip variable on 1 for that dimension. We're going to use a ternary operator for this. So we're going to go something like if psx equals 0 and 1 or 0. And the same one for the thing at the bottom here, psy equals 0, 1 or 0. So this allows us to have the slippage now occur as well when we are moving horizontally. Now you see we still get caught on the bushes, right? We can obviously increase the slippage now. We can increase it to like 6. And that will make it so much harder to get caught on these things. We still can get caught, but it's so much harder, right? But now also with that slippage is very jarring. So let's bring it back to 3, because this is what I figured out Zelda looks like. Alright, so one final correction that I noticed while I was editing this video. I kind of assumed throughout this video that in Link's Awakening, when the corner slippage occurred, it would be like a rigid snap into the position. But looking close at the footage now during editing, I noticed that it's actually a gradual slide. And so in order to achieve this, what you need to do is basically you go in here when you apply the slippage, and you can just wrap those variables into the sine function. And that will make it so that the slippage is a bit more gradual. Now, under those assumptions, I would actually also rethink this entire loop, but for now that works well. So this gives you a little bit more gradual movement. It's still very subtle. Now, this gradual slippage actually allows you to increase the window of the slippage a bit more, and that doesn't look quite as jarring anymore, not as sudden anymore. So now you can get those really nice rounded bushes. But that's not what we have in Zelda. In Zelda we have 3, so we reset it back to 3. So yeah, we still get stuck on obstacles, obviously. We still sometimes get stuck on obstacles. Sometimes we don't, sometimes we do. But also this is one of those cases where the problem starts spilling over into other areas of the game design. In Link's Awakening, the obstacles are sometimes things you can interact with. You can lift pots. You can push stones. So in many ways, you actually do want to get stuck at some of those objects eventually to interact with them. Picking up the pots would be very difficult if you would always slip off of them. We haven't recreated this part of the game, so maybe we're also judging this collision without having the full picture in mind. But also we had to write a lot of complicated code for pretty subtle effects here, right? Looking back at the 4 levels, I'm once again wondering if it's even worth it. Over the course of this video, I talked about how many different games solve this issue in different ways. Recreating the movement in Zelda has been a fantastic exercise, but that doesn't mean that this final version that we arrived at is the ultimate version, the best solution for any game. Depending on what kind of game you have in mind, and depending on what kind of complexity you're comfortable with, an earlier level might be just fine for your game. Don't be pressured to go all the way just because Zelda does this like this. And also I might have gotten something wrong, or maybe even you have a good idea of how to push things even further. Let me know in the comments section. But yes, this is fantastic. This is exactly what I see when I look at the footage of Zelda. This is truly the movement of Zelda Link's Awakening. As a little treat, let's add a little bit of code to make those flowers animate. It's an easy little effect. I'm going to create a shortly and small variable that will count the frames, because in the real Zelda games, the frame of each flower is being shown for 20 frames. So here in a draw function, we advance the t frame timer by 1. And here in the update function, if t frame modulo 20, so every 20 frames, we loop through the map, and we're going to get the tile at this position. Like this. I made a mistake here. And now when you check the numbers of those tiles, it's between 37 and 40. So if TLE equals 37 or equal 39, then we're gonna change this tile to 1 more. So TLE plus 1. Now if you're right at the end, then we cycle back to the beginning and we set it back to 37, double equals. Let's run this, and there we go. Isn't that nice? Isn't that nice? Let's remove those debug points. Wait a minute, there's one little tweak here in the check buttons function. When we check if a button was pressed, if no buttons was pressed. We did this last time around and we deleted this. If no button was pressed, we need to set the animation counter to 7. So pani t equals 7 and pani frame equals 1. Because we want to have those tiny little steps. That's what we're looking for. Now it looks truly like Zelda. On my previous videos, I spoke how I dislike, these kinds of and then draw the rest of the owl kind of tutorials. And if I leave things like here, it certainly would be that kind of video. So most importantly, let me know down in the comment section where to go next after this video. What do you want to see next? Do you want me to continue with Link's Awakening and tackle stuff like transitioning from one screen to another, or sword fighting? Or would you rather see me recreating other games and other cool effects like, for example, Pokemon with their endlessly scrolling overworld map? Or would you want me to switch this to a different engine like Pico-8 and try to recreate a more advanced Zelda game like A Link to the Past? I will review the requests in the comments section and decide what the next video is going to be about based on that. But for now, the code for all 4 levels from this video will be down in doobly-doo as always. And so all that is left for me to do is give a huge big thank you to all of the people who are supporting this show on Ko-fi.com once again. One thing I haven't done in a while is give shout outs to new supporters, so let me catch up. A warm welcome to all the new supporters, including Firepire, Sebastian Van To, Ekran, Schmentz, Noah Constrictor, Kane, SPU, Tom Kirby Green, Diffradev, Jeremy, Grimbrim, Dennis, Kiffin Gish, Yaman, Philip, Shimster, Ari, Maya, We the Squeamish, Dr. Paneas, and Arminado. And also big thanks to one-time donations by Richard B.S., Duddy Funk, David Mestner, Gian Joff, Michelle, Tim, Sasha, Mo, and DSP. And especially warm thank you to longtime supporter Meets for his recent generous donation. Thank you so much, Meets. And for anybody else who wants to become a supporter and wants to have even more of a say of where this channel is going, the address to become a supporter is coffee.com/lazydevs. And this is it for today. Look forward to more Zelda videos in the future. For now, see you next time around, guys. Bye bye.